I'm extremely excited to be here. I think we had an amazing conference so far, and I'm especially happy that I can share one of my really favorite topics today with you, which is about Elasticsearch, together with Tapestry NEOS. So, about myself, I'm Sebastian Kurfürst. I'm currently 26 years old, in the Tapestry community since quite some time. Most of you probably know me because you've heard about me because of XBase or Fluid. Most recently, I've been more working in the direction of TypeScript and also a lot working with Elasticsearch. In my professional life, I'm the co-founder of a company called Sensor Media. We are currently 5 people, and we are 7 people. We are all around here. You've probably seen us on the t-shirts. And we do web applications. We do consulting for web applications, not just on the PHP stack, but on all kinds of platforms and all kinds of problems. And we also, of course, do, for instance, NEOS coaching, consulting, and also bug fixing. And we've been releasing a product here at the InspiringCon, which is called XPly, which is a business intelligence and enterprise search solution targeted to small and medium enterprises. I basically don't want to show anything about that. The only reason why I explain that is because this is all based around Elasticsearch. And that's how we're getting closer to the core topic, what we are going to talk about now. So we have been using Elasticsearch in lots of different ways, basically. So let's talk about search. And in order to do that, it makes sense to first look at how we store content in Tapestry NEOS, because essentially we would like to search in Tapestry NEOS. So if we look at the storage of data in Tapestry NEOS, you all know that we use the Tapestry content repository to store the data in the system. And just as a quick recap, this content repository stores the data in a tree-based structure, essentially. So the individual elements, they're called nodes, and these nodes comprise the structure of your website down to the single element. And actually, the content repository is really, really great for tree traversal, which means get to a certain point in a tree, find some subtrees, traverse the tree up, all these kind of things. But it turns out that this is only half of the story, actually, because at some points you also have other use cases. For instance, you want to know all articles written by me, for example, or by anybody else of the core team. Or you would like to display the first 3 locations tagged with a certain tag, for instance, with conference location. Or you would like to see the newest pages in a certain category. And it turns out that if you try that with the content repository at the current point in time, that's actually not that easy, because the tree as a representation is not what we want at that point. Instead, what we want is basically we want to get rid of the tree structure and rather think in sets, which is mathematical sets where all the nodes are located. And basically we have a big pile of data in our system. That's like the second view of our system. And with the search, we would like to extract the currently relevant content from all the documents we have, from all the documents and all the content we have in the system. So that means that's a completely different topic than tree traversal, because it doesn't matter where in the tree the content is stored at that point in time. We basically just want to filter the whole data set. And now I'm going to tell you a dirty little, not so well-kept secret. Actually, the Tapestry content repository is currently not so really good at providing this set-based view. It's really good for tree-based versions, but it's not really good for the set-based view. So that's where search comes into play, and as I'm going to show. So now we are going to see, I'll walk you through the basics of Elasticsearch and the integration of Elasticsearch together with NEOS. And in order to understand a little better how, well, where you are, what your background is, I would like to know who's using Elasticsearch or has used Elasticsearch already. Okay, quite a few people. Who has used Solar? Okay, some other people, so that's pretty cool. Right, so who has used it in combination with NEOS, by the way? Okay, also a few people, very nice. So for all the others, what you need to do is you need to download ElasticSearch. It comes as a zip file, you extract it, and it runs totally self-contained. You just need a Java virtual machine on your machine, so that's pretty easy. And ElasticSearch is basically configuration free, which means there's only very little things you need to configure in order to use it together with NEOS. And this is, just for reference, I won't explain that in detail. What this essentially does, it enables some special features in ElasticSearch which make indexing together with NEOS really performant, which is called dynamic scripts. This is like the top part of the section. And the second part of the configuration is actually to make Elasticsearch secure by default, because Elasticsearch, it has the name Elastic in, which means that it can grow and shrink dynamically depending on the data load. So it has clustering built in, it has auto-discovery of other nodes built in. And if you download Elasticsearch on your computer and you start it 2 times, these 2 Elasticsearch instances will automatically connect to each other and replicate the data, which is really nice if you're on a really big setup, but of course if we just index the usual website, that is actually a big security hole, because Elasticsearch will scan the network for other Elasticsearch instances, and we don't want to replicate the data all over the world or all over the data center to other nodes basically. So that's why you should use a custom cluster name, which is really unique. We usually use random strings for that. We only want to listen to localhost. And because we don't use replication in the first steps, we can get quite some performance benefits by the last 2 settings, which I won't explain in detail here. So first, this is all the configuration you need to do after you've downloaded Elasticsearch. So if you start it, there's a command which is called bin Elasticsearch in there, and if you start it, it fires up its own web server, and it starts on port 9200. So if you open it up in your browser, you get some status indicator, which is basically some JSON string indicating the servers are right, some names of the server, and all these kind of things, version information. So that was Elasticsearch. Now we, of course, need to do some things to our NEOS instance to connect them together. And actually, for various reasons I'll explain later, the search functionality is built into quite a few separate packages. And in order to install them, you basically need these 2. The first one is just common functionality, which we need for all search implementations. And the second one ties the content repository together with Elasticsearch. So that is like the main one. And I'm a core developer, so I'm usually using the current development master. That is what this dev is about. If you leave it out, you get the latest stable version for Elasticsearch, and the editor, the last one I think has been released 1.5 weeks ago. So it's pretty much up to date currently. But as time progresses, of course, newer features will be in the master. And if you just install that to your NEOS instance, you get a few extra commands on the command line. The most important one being flow node index build, what you see here. If you run that, it will automatically connect to your Elasticsearch instance, and it will basically index the whole data in your content repository and make it available for searching. So we just run that command and we forget about that whole thing. Now I would like to show you what is actually in the Elasticsearch index, and there are 2 extremely valuable plugins for looking at the data in Elasticsearch. I don't know, do you know these plugins? Head and Sense? Okay, so that's really, Elasticsearch has a plugin system, and you can use these plugins to have basically debugging frontends, to add debugging frontends to your Elasticsearch instance. And the 2 ones we are using most is the Elasticsearch plugin, Elasticsearch Head plugin, and the Elasticsearch Sense plugin. And by these 2 lines, basically you install it. The rest is just the output while installing. And then, if you go to these 2 URLs, you'll get you'll see the front end of the plugin. And we'll now check out the Elasticsearch Head plugin. So if you open it up, basically you see an overview about your Elasticsearch cluster. We see it's currently about 3.45 megabytes in size. It has 968 documents in there. I think currently it's a demo site actually. And what is mostly interesting for us currently, if you switch the tab to the browser, we get a data view of what is in the Elasticsearch index, We can also click an individual row here, and what we see then is a JSON document, which is what is indexed in Elasticsearch. So this is exactly the thing which has been put into Elasticsearch once you run flow node nx build. So that's just for getting an overview and for seeing how the data gets put into Elasticsearch. So of course you want to have some search form on your website. This is what we didn't talk about yet. And we think that search plugins, or we can imagine that for different use cases, quite a few different search plugins will need to emerge. So that's why we just provide a simple plugin in an extra package. So you're totally free to create your own search implementations, to really customize it to your needs, which is especially helpful for bigger websites. For smaller websites, it's really just, you can just use that one. And if you install that, you get a new content element, you can add a search plugin to your website. And what you get is basically this. So you get a search form. If you enter something in, you get a result listing from the different, so that's basically a full text search of our website. We see the result highlighted, and we see where actually the result is in the path of the website. Right. So this is full text search. That's basically it. The interesting part here is that we index the node data directly, as you will see later. So the full text search is really nice, but if you imagine, or if you remember the use cases I've started with, which are like find the most recent 3 posts of my website, we can't use full text search for that, right? We need something else. So what we want to do is we want to query for nodes in this index. We want to use the set-based view which Elasticsearch provides, and we want to query for some nodes based on arbitrary criteria, how we'll see in a bit. And in order to show that example, I've made up a small example how this works. In my case, I have created some document node types, one which is called category, so that's like the super category. One is called article, and the other one is called tag. So basically, this is a simple news website you could imagine. So articles are news articles. They are in one single category, and they can be tagged with one or multiple tags in the website. And I'm now going to focus on the view of a tag where you can click a tag and then see the most recent articles which are tagged with that tag. So you see in most websites, or in many websites which use tagging, you can show a list of all the tags associated with a given article, for instance. And if you try to do that on the node tree, that's actually pretty difficult to do, because if you look at that, the tree is the category and article tree, and then we have cross-references towards these tags, and that makes actually searching in an efficient way, just with a standard Tapestry content repository, pretty difficult currently. So what do we need to set up? The first part is an extremely, that has nothing to do with search basically, but this is how search becomes powerful. As you know, the Tapestry content repository is essentially a tree of nodes, but on top of that we have built a feature which is called references, where you can link other nodes with each other. So basically it's a tree of nodes, and then there are cross-references between arbitrary of them. And in order to configure that, you go into the node types YAML where all your node types are configured. For the news article, we for instance say, okay, there's a property tags which has the type references, and we only allow links towards this tag node type. So that means in the auto-completion you can only search for tags. So this in itself has nothing to do with search. This is just to set up the prerequisites and make sure that we can actually associate tags together with articles in NEOS. If we now want to render the tags overview page, we basically want to replace the main area of the website, and we can use TypeScript for that. And we do that by adding a new condition to this primary content prototype, where we say, okay, for all news tags, we use the TypeScript object called with the same name to render the output. So don't worry if you don't see all that in detail. That's just for reference so that the example is complete. That's really just for making sure we can use Fluid to render the text overview page. And then we have a custom type. By that setup, we can write a custom TypeScript object, which is in this case also called the tag TypeScript object. And this, by default, inherits from Fluid, so it has a Fluid template which contains all the HTML output. So what we now need to do, we need to get data into this template, right? We want to know, and the main data we need to get into this template are the latest articles tagged with the given tag, actually. So if we have, basically in Fluid, as it works this way, that on the left side you write a variable which you can access in Fluid, and on the right side you can output a string or an EL expression, and actually this is what we are going to focus on in the next few minutes, because that's how you'll see how the searching actually works. So, if we, this is actually a real-world example. I'll just explain it quickly and then go through the details. So what we essentially do is we start the search at a certain point of the website, which is currently the site node. So that means we search throughout the whole website. This is basically a global search throughout our whole system. We could also search for parts of it. And then we add constraints to the search expression. For instance, we say we only want to find certain node types. We only want to find the article in our case. And we want to find the article where the text property has our current tag in there. So this is this exact match line here. The current node is the current tag we are rendering. And the tags is the list inside the news article, and we want to basically do an exact comparison there. Then we wanted to show the first 3 results sorted by publishing date, and in the end we execute the query. So basically what you do is you set up this search query object by calling search.query in EL. Then you can add constraints to your search query depending on what you need. So what is in here in the middle, that totally depends on your use case. And then with execute, you run the query. And now in the template, we can actually use the variable we've just assigned into the template. So we, for instance, we could iterate over the latest articles tagged with a certain tag, and then render a link towards the single article, and then render it however we want to. So. And the most magic happens in these operators in here. So just as a side note, I've shown you this full text search in the beginning, if you remember. Internally, this is also just a TypeScript object, as you've just seen. The only difference is that we use this special full text constraint on the search result. And this actually does a fuzzy string search, essentially, which is what you would expect from a full text search. So basically, the search plugin which you have seen is just very little HTML Fluid template, a little TypeScript, and just calling and wiring the components together, which makes it very easy to create your own versions of it, to fork it, to use it for whatever reasons you want. And basically, the node references on the one side, together with the search queries on the other side, they together provide these set-based views on our data which we need for bigger websites. That's basically it. I'm now going to dive into some core concepts of Elasticsearch, just to give you an overview how it works on a more internal level, because what we've seen so far helps for getting a basic search up and running. But usually if your site is growing a little bigger, you will want to fine-tune the way the indexing works and the search works. So that's why it's pretty helpful to get a little understanding about how Elasticsearch works actually, and so that you can fine-tune it to your needs. So in a relational database like MySQL, for instance, you normalize data very much, which means that you want to reduce duplication in your data here. A single data element, a person, a tag, an article should exist exactly once in our database, because if we want to change it, we only want to update a single place, essentially. And this is what we call normalized data. In an index, on the other hand, which is what Elasticsearch is, it provides you an indexing functionality. It is very common to denormalize the data which is stored in the index, which basically means that instead of one table here and then in another table these three elements and linking them together somehow, we basically create three objects which get the A directly, the first part directly joined to it. This might first seem weird if you come from a relational database background. But the thing is, what we essentially do is we trade indexing, or we trade update performance for read performance. What we want in a search index is extremely high read performance. And we achieve that by denormalizing our data in a way which suits the queries we want to do later on. So that means that while a normalized data in a relational database, there's pretty much just one way to do that. Well, I mean, more or less, like if you should build an object model for what you've seen so far, most people of you will result in the same domain classes in the same database structure, more or less. And in the search case, it can very well happen that everybody of us creates a different way the index is built, because everybody of us has different use cases how the querying should actually work. So that is just very important to remember. And because we denormalize the data at that point, it is very important that Elasticsearch will not be the primary source of information. Basically, we must be always able to throw the index away, start from our node tree, which is essentially normalized data in some way, and re-index the whole set together. So that is just very important because there are some occasions where you have to drop the Elasticsearch index and start from scratch essentially again. And the package makes it actually really easy to do so, because you can just call this node index build all the time and it will just work. Okay, if we actually look at an example of what is in our index, we can do so by calling a certain URL in this in our system. And the basic in Elasticsearch, there are essentially three hierarchy levels. The first one is the index, the second one is the type, and the third one is the document ID, which is, or the document itself, which somehow corresponds to an index being a database, a type being a table, and a document being an individual row in this table. But you don't have joins. So that is the basic data format of Elasticsearch. And if you retrieve a single document, then you see the data which is in there. And if you look at it closely, you actually see the denormalization at work. So we have some fields which we add automatically for efficient querying, which is called parent path, for instance, which contains all the parents up to the root for the current node. And the reason for that is, by doing that, we can do extremely efficient queries on subtree matches. So we can extremely quickly calculate whether a certain node is inside a subtree of what we want to of a certain other node or not. And this is for us really important, and that's why we've built the index this way. And of course, there's some duplication here, but for us this isn't really a problem, because as said, we can just re-index the whole data set if something changes, or we can re-index individual documents if something changes. A second thing you might wonder about is we have these simple properties like identifier, workspace, hidden before date, the text, which you don't really see anymore, and which are just simple strings or booleans or so. And then we have some properties which are arrays. And essentially every data field in Elasticsearch is an array. So basically this identifier at workspace and path and so on, which look like simple strings, is essentially an array with just one element. Why this is the case, we'll see in a bit. So for now, just remember we have these three categories. We have indexes, types, and document IDs, and that's basically how it works. And in a relational database, you have the table schema, which defines which columns are in your database. There's something roughly similar in Elasticsearch, which is called a mapping. A mapping essentially says or gives information about the way the data is structured. And you can basically start with just throwing arbitrary data into your Elasticsearch index, and the mapping will build up on its own. So this will automatically happen if you insert JSON data to your system. But for more advanced use cases, you will want to control that in detail, so that's what we do by default, because you will want to modify this mapping in detail, as we'll see in a bit. And if you look at the way the full text search is implemented, for instance, if you look at a document, so this is the node type page we see currently. There you see there's this special key called full text, and in there is this H1, H2, H3, H4, H5. The idea with that is that we want to boost, or if there's a match in an H1 heading, which is extremely important, extremely bold on the website, this is much, much more important than a match in an H3 heading or in the normal text. And this can be controlled in ElasticSearch using this boosting, which essentially says this is a lot more important than this, and this, and this, for the one side, and for the other side, by including all the fields in this one single index, in this one single field, which is called all, which is a nice feature to do this actual full text searching. Right. I said before that we can that we have to always be able to throw away the ElasticSearch data and rebuild it completely. And of course, it would be a pretty big customer experience if you imagine you have a bigger website. The rebuilding takes a few hours. If you trigger it in the middle of the night, in Germany at least, and then the search won't work for a few hours, or even the core functionality of your website doesn't work for a few hours. Because remember, you actually, for bigger websites, for magazine-style websites, for instance, you will use this search feature almost as often as you traverse the content repository. It's an extremely common operation you will want to do. So what we actually do is we use a feature so-called index aliases. That means this Tapestry CR is essentially an index alias to this long Tapestry CR minus the current timestamp of the index when it was created. And it's like a symlink in the file system, essentially. And if we want to rebuild the index, we actually rebuild the index completely anew. So that means the command line tool will index this one, fill this one, but the website will still use the old one for reading. And once everything is finished, basically the pointer is switched, which is an atomic operation. So there's, and from that point on, all the queries are redirected to the new index. And that's actually a pretty powerful concept, because you can not only reference just one alias, one index with such an alias, but also multiple ones, which is helpful for advanced cases. Okay, now that was like the basics, like how is the data in the system. That was the basic data model of Elasticsearch. Now let's look what happens when we actually index a string. Remember, we want to do full text search. So let's say at some part of the website there's the string Hey InspiringCon 2015, and this string is first split into tokens. It is split at white spaces usually. So you see Hey InspiringCon 2015 is split into 3 tokens. And then there's a filter pipeline. This filter step, for instance, has removed the comma on the left side. Then another filter step might lowercase the whole stuff, for instance. And what we get at the end is a bunch of so-called tokens, which will be used for searching later on. So that means during the indexing, this string is broken down into these individual ones. And of course, if you imagine this, if you have a long text, then you will get a lot of tokens. But that's not a problem, because Lucene and ElasticSearch have been optimized for exactly that use case. So what happens now when we search? Let's say I'm searching for InspiringCon 2015. I didn't put a white space on here, but I still expect it to match. We don't only have this pipeline on the searching step, on the indexing step, but we also have such a pipeline which is used for the search queries, which is called the search pipeline. So this means we have the same tokenization step, which will split it on the number, for instance, which is also already built in ElasticSearch. That is basically the default behavior what will happen, and then also the lower casing, for instance. And basically, what we get then is a bunch of tokens in here. You know, this is what is in the index, and this is what we are searching for. And Elasticsearch essentially only does a simple string comparison. It basically checks if this 2015 exists here, if this inspiring con exists here, and because it's really just a simple string comparison, it's extremely fast and extremely performant. That's basically the whole trick which all indexing engines do. And the nice thing is that through customizing this indexing or the search pipeline, you can do very advanced things. For instance, you can remove, if you have text in a certain language and you know the language in advance, you can remove or you can create tokens which only consist of the root of the word itself without the endings, for instance. So that if you index verbs, for instance, they will also always indexed with the normal form of the verb, which drastically can increase your search performance or your recall precision, essentially, so the search precision. So that's basically how the searching works. Essentially, just these two pipelines, and in the end, it's either a simple string comparison of the tokens or a prefix match. That's essentially the two operations which can be done really efficiently. And once that is done, depending on how many matches we have in our documents, the higher the documents get ranked. So that's like how the scoring is built. Okay, you can also try that on your own. There's Elasticsearch is very well scriptable, has a very good API and a very good HTTP API. And so if you go to this analyze endpoint _analyze, and you can add some text like this, hey, it's Byron 2015, and then you get the tokens out which the system will create inside. And that's a very good debugging tool if searching doesn't turn out to work the way you expect it to be. And that is now the default pipeline, but you can also customize that, of course, and try individual steps. So that way you get really a good insight into the individual indexing steps and also the individual searching steps. And all the time, if you change one of the pipelines, then you essentially need to rebuild the index again, because if you change the search pipeline, then all the data in the index is essentially stale. We need to re-index them to get it up running. So that's why it's important to not use Elasticsearch as the primary data source. Now we've seen the basic idea about how the data gets into the system, how we manage the schema. What we've not seen yet is how an actual search query will look like. And I'm just going to show you a real example. For instance, you can, if you have such an expression like this full text search, which is from inside the search plugin, for instance, you can just add this .log operation to that, and by that you will automatically log all the Elasticsearch queries before they are made and after they are made, and get debug information inside the data logs Elasticsearch log. And basically you get query log, which is a long JSON string from here to here. Don't read that in detail, we'll go into that now. But basically you copy paste this JSON. Then you go to the second plugin, which I've shown you in the beginning, which is called Elasticsearch Sends. And what this essentially does is it's a pretty nice HTTP client, essentially, where you can make a query to this Tapestry search endpoint, and then you can just copy paste the whole query in. And of course, and there's also functions up here which are very convenient for auto-formatting this. And so this is for debugging. Basically, you copy paste the query which is done in the real system, and you try it out here. And then when you run the query up here, you see the results on the right side. So that is what we really often use for debugging. If something doesn't work, we basically check it here. We reduce the query to the most minimum parts, and then we see if everything works or not, and then we can fine-tune it and get it all back into Elasticsearch again. And as you see here, the query itself is essentially a big JSON object. So it's not a string like in SQL or how it was in Solar a few versions back. I'm not sure how it is currently. But in Elasticsearch, a query is a huge string, essentially, a huge JSON object, essentially, which makes it very easy to compose a query together out of different parts. And this part, for instance, is a Boolean query, which has this part and this part. And here we actually do the full text search. So this is what we enter into the search field. And then we have some filters which say, okay, we only search inside a NEOS demo type 3 org website, for instance. And basically the operations in EEL, which you've seen, they just add parts to this big query at various points. And that's how they are manipulated. So for instance, there are also parts to say, well, only give me documents, give me nodes, which are not hidden, which are inside the valid range. So that is all parts of the query which we automatically add, of course, because that is pretty useful, I mean, in our case, to not show invisible content, for instance. Right. And that is, now we've seen the basic workflow. We index documents, in our case nodes, into the system, and then we customize the indexing and the search pipeline, and then we essentially can do a full text search using this JSON-based search language. And what you will get out of that is always the individual documents you have indexed at the first place. So that, and then ElasticSearch people found out that they have a real big data treasure in their system because it contains lots of data. So that's why they have a special feature, a specially built feature, which is called aggregations. And this can be used to calculate statistical information about the current result, which we, for instance, use in our tool to display some facets, which you could also use in the search plugin, which Kibana uses to index logs, for instance. This is all based around this aggregations feature, which is extremely powerful. This is not yet used in the search plugin or the NEOS or Flow integration yet. Because we are, I'm totally open to add that, but it really, we just need a use case, a concrete use case where we would like to use it, and or where some customer would like to use it, and then we can add the first parts into that direction, which make it possible to calculate statistical information about our current search result, which is valuable for bigger websites. So that was now some ElasticSearch in depth, how does it work. So now now with that background knowledge, you can get back to NEOS and ElasticSearch and you can start to fine-tune it. And essentially, to fine-tune ElasticSearch, we need a way to manipulate the mapping, which is like the SQL schema, basically. And there's a command line tool called Flow Node Index Show Mapping, which shows you the current mapping the way Flow sends it to ElasticSearch, or NEOS sends it to ElasticSearch. So that means the master of how your data is structured is in NEOS itself. And this mapping is actually created from the node types and the node types.yaml. And there are some defaults in the settings which for each data type add some basic mapping, and then you can override it on an individual node type level for individual properties, and that's basically how you can really fine-tune the whole indexing process and the whole search process. And second, we need a way at some points to denormalize data, right? I mean, creating the mapping is the one thing, but the second part is to calculate the data in a way which we can use for efficient querying later on. And for that, inside this configuration, we have a part called indexing, which is an EEL expression, and there you essentially specify what gets loaded into the system. And this can be pretty powerful. For instance, there is a function which calculates all the path prefixes we've seen in before. So this is what we use internally. That's nothing you will use, but this is how we internally denormalize certain parts of the data in the system. And one special detail for full text searching, how it works in detail, is if we look for nodes, then we can get back all kinds of nodes, like text and images and all these things. For full text, of course, it doesn't make sense to just return a single headline. We always want the whole document, the whole page where the content is. So that's why, for instance, we want to, if text is in here and in here, which matches, we still want to return the whole article about us. And that's why ElasticSearch, the ElasticSearch integration, collects all the content in the lower nodes, in the content nodes inside the main article. And this is called a full text route. And what you can do then is to fine-tune and say, okay, the headline maps to an H1, so this goes into the H1 bucket, which is really important. For the full text, we map that to H2, to the paragraph, to the normal plain text essentially, and this can be fully customized how this mapping works. And that's just for reference, so that's how you specify a document. This is all internal, that's nothing you need to do. And this is how the full text extraction is possible. So that's how you extract the full HTML, this is how you put something into the H1 bucket. That's basically just for reference if you want to look it up. For additional data, it's pretty simple. You just add an additional index to this alias. So for instance, not just the Tapestry CR, but the products CR. And this is actually not yet built in the Elasticsearch plugin core, but it probably will be very soonish. As far as I've heard, it might be some project which would benefit from it. So that might happen pretty soon. There are some more advanced features to pull data into the system. So there's a feature called rivers, which can pull data from the system. So for instance, there's a Twitter river, which directly indexes Twitter streams without you doing anything. So Elasticsearch pulls the data, which is pretty nice. And if you now heard all that and you think, well, okay, Elasticsearch is pretty nice, you really want to, you actually want to use it, but you only have a small website, and of course you need to have a server ready, you need Java running, you need Elasticsearch running, so there are quite a few additional components which come because of Elasticsearch. So it might very well be that Elasticsearch is actually way too big for your project. And that's why Christian built a really cool alternative, which is called Simple Search, which you can install using that line just instead of the standard Elasticsearch package. And this will use an SQLite database for indexing, which is really nice for small websites. So that's nothing you'll use on your big multi 100,000 nodes website, but just for small websites, that's pretty convenient. And you still have roughly the same API which you've seen before. In future, I think so this is still being developed, and essentially we are developing the package depending on individual needs. I would really like to support aggregations, for instance. I would really like to support additional data sources in a better way, so that, for instance, you can add, through another mechanism, add your Magento data to another Elasticsearch index, your products, for instance, and still use this mechanism for displaying the results and showing everything. If you want to know more, I think there are two ways to learn all that. The one is the Git repository in the Flowpack Elasticsearch content repository adapter has a README which essentially explains everything you've seen in the slides here. And the second part is Elasticsearch has a really, really good book published by O'Reilly, and this book is also available online for free under this URL. So it's perfectly legal, don't worry. And they explain really the core concepts of Elasticsearch in a really, really nice and understandable way. Yeah, so what perhaps we've seen in this talk, basically it's on the one side how we get data into Elasticsearch, and then how we can efficiently query and index that. Okay, thank you very much. Is there time for questions? Questions?
Yes.
Currently there is no support for content dimensions. Have I seen this right?
Actually there is. In the current master they are supported.
Okay, so you have different indexing things for German and English and so on?
Yeah.
Stem-word filtering, stop words and so on?
Well, I'm not sure on that level actually. It might be that this is not supported yet, but if we find the first projects which actually need that, then we could add that for sure. Yeah, so the data is indexed in the right way, but you're not yet able to configure individual indexing settings for different dimensions depending on language, for instance. That is not possible currently, as far as I know. Okay, more questions?
I was just wondering, what about restricted content? Like,
restricted content?
Yeah, now that we have the ACLs, we have to cater for them.
So basically, all the results you've seen, we search the data through Elasticsearch, and then we still fetch it from the content repository when we exactly know where it is located. So this means all the restrictions are totally put into place. They are used basically, but in the longer run, it could be possible to just directly convert such a policy configuration into an Elasticsearch filter, which restricts the query in a further way. So that would be the more long-term idea, which is the higher performance way. More questions, if we still have time?
I was thinking about, you showed a query in TypeScript, and this is a static query, I suppose, that you define when you program. How if you want to make a query dynamically at runtime?
I mean, basically, this query was not fully static because there were points in this query which were entered by the user. So usually you don't want the full query configurable until the front end, but just some parts of it. So in our example, we have the current tag was dynamic, the current search query string was dynamic. So you can also easily have a text field, for instance. You could easily build a text field in the inspector where you could insert exactly this query. So that would be also feasible if that fits your use case. Yeah. Okay, more questions if we have time? Or? Okay.
Right. So thanks again to Sebastian Kurfürst. Give him a hand.
Thanks.
Thank you very much.